Welcome to this coding walkthrough. In this session, we'll explore LeetCode problem number 905, sort array by parity. The challenge is to rearrange an array such that all even integers appear before all odd integers. We'll dive into the problem details and discuss efficient ways to solve it. Let's get started. In this problem, you're given an array of integers called nums, and your goal is to rearrange the array so that all the even integers appear at the beginning, followed by all the odd integers. The output can be any array that satisfies this condition, meaning the relative order of numbers within the even or odd groups doesn't matter. For example, you don't need to worry about maintaining the original sequence of even or odd numbers. As long as all evens come first and all odds come after, the solution is valid. Now, let's look at the input and output format. The input is a list of integers, nums, and the output is a rearranged list of integers where all even numbers precede all odd numbers. This ensures the array is sorted by parity, but without requiring any specific ordering within the groups. Keep this flexibility in mind when thinking about potential solutions. Let's take a look at some examples to clarify the problem further. In the first example, the input array is 3, 1, 2, 4. Here, the odd numbers are 3, 1, and the even numbers are 2, 4. A valid output would be 2, 4, 3, 1, or 4, 2, 1, 3, as both rearrangements place all even numbers before the odd numbers. The relative order of numbers within the even or odd groups doesn't matter, so there are multiple valid solutions. In the second example, the input array is 0. Since the array contains only a single even number, it is already sorted by parity, and the output is simply 0. Finally, in the third example, the input is 2, 4, 6, 8, which contains only even numbers. Any permutation of this array, such as 2, 4, 6, 8, or 4, 6, 2, 8, satisfies the parity condition because all elements are even. These examples highlight the key requirement that all evens must come before all odds, regardless of their original order. Now, let's go over the problem constraints and consider some edge cases. First, the constraints specify that the length of the array, nums, will be between 1 and 5,000, and each element in the array will be a non-negative integer between 0 and 10,000. With this range, we know the input size is manageable, and we don't need to handle negative numbers. For edge cases, consider arrays with only one element. If the array has a single number, the output is simply the same array, as it already satisfies the parity condition. Another edge case is when all elements in the array are either even or odd. In this situation, the array is already sorted by parity, so no rearrangement is needed. Finally, for arrays with mixed even and odd numbers that include repeated values, remember that the evens and odds should still be separated, but the relative order within each group is irrelevant. These constraints and edge cases will help guide your approach to solving this problem efficiently and correctly. To solve the problem of sorting an array by parity, our goal is to rearrange the array such that all even numbers appear before all odd numbers. One straightforward way to approach this is through a brute force method. The intuition here is simple. We traverse the array, categorizing each number as either even or odd, and store them in two separate lists. Once the traversal is complete, we concatenate the list of even numbers with the list of odd numbers to create the final result. This method has a time complexity of O(n), as we make one pass through the array to classify numbers and another to concatenate the lists. However, it requires additional space proportional to the size of the array to store the two separate lists. While intuitive and easy to implement, this trade-off in space usage makes it less ideal for situations involving large inputs. An alternative and more space-efficient method is the in-place two-pointer approach. Here, we use two pointers, one starting at the beginning of the array and the other at the end. The idea is to increment the first pointer when it points to an even number and decrement the second pointer when it points to an odd number. If the first pointer encounters an odd number and the second pointer encounters an even number, we simply swap these two values and adjust both pointers. This process continues until the two pointers meet. The beauty of this approach lies in its efficiency. It processes each element at most once, resulting in a time complexity of O(n). Additionally, since no extra memory is used, the space complexity is O(1). This makes it particularly suitable for scenarios with large datasets. However, it does modify the input array directly, which might not be desirable in certain situations. Another way to solve this problem is by leveraging Python's built-in sorting functionality. Using a custom key function, we can prioritize even numbers over odd numbers during sorting. For example, by using sorted nums key equals lambda XX%2, we ensure that all even numbers come before odd numbers. While this approach is concise and easy to implement, it has a time complexity of O(n) log n due to the sorting operation and a space complexity of O(n) for storing the sorted result. This makes it less efficient than the linear time solutions. Despite its simplicity, the sorting-based approach is slower and consumes additional memory, so it is generally not the preferred method for this problem. Ultimately, the in-place two-pointer approach stands out as the best strategy due to its optimal time and space efficiency. By swapping mismatched values during a single pass, it avoids the overhead of creating additional lists or performing a sort. The key insight that simplifies this problem is recognizing that even numbers are those for which number %2 equals 0, while odd numbers satisfy number %2 equals 1. Additionally, the problem does not require preserving the relative order of even or odd numbers, which allows us to use in-place swapping to rearrange the array efficiently. By addressing mismatched values directly, the two-pointer approach minimizes both time and space complexity, making it an elegant solution. However, it is important to note that this method modifies the input array, which might be a drawback in cases where the original array needs to remain unchanged. On the other hand, the brute force and sorting-based methods, while easier to understand and implement, come with trade-offs in either space or time efficiency. In conclusion, the in-place two-pointer strategy strikes the best balance between simplicity and performance, making it the most practical choice for solving this problem, especially when dealing with large inputs. The problem we are tackling here is LeetCode number 905, titled Sort Array by Parity. The goal is straightforward. Given an integer array, we need to rearrange it so that all even integers come before all odd integers. Now, the order of elements within the even group or the odd group is not important. To solve this efficiently, we'll use the two-pointer approach, which allows us to rearrange the array in place without requiring extra memory. This method is efficient, running in O(n) time. To begin, we initialize two pointers, left, starting at the beginning of the array, and right, starting at the end. The left pointer identifies odd numbers that are misplaced, while the right pointer identifies even numbers that are misplaced. This setup ensures we can detect and swap elements as needed to achieve the desired arrangement. Next, we iterate through the array as long as the left pointer is less than the right pointer. During each step, we examine the values at these two pointers. If the value at left is even, it's already in the correct position, so we simply increment the left pointer to move forward. Similarly, if the value at right is odd, it's also in its correct position, so we decrement the right pointer to move backward. However, if the value at left is odd and the value at right is even, these two elements are swapped. This swap ensures that the even number moves to the left side and the odd number moves to the right side. After the swap, we increment left and decrement right to continue the process. The iteration stops when left is no longer less than right, signaling that all the even numbers have been moved to the left and the odd numbers to the right. At this point, we return the modified array, which now satisfies the problem's requirements. There are several key insights that make this approach effective. First, by using two pointers, we minimize unnecessary operations and avoid allocating additional memory, keeping the space complexity at O(1). Second, the algorithm rearranges the array in place, directly modifying the input array without any extra storage. Third, the efficiency of this method is notable, as each element is processed at most once, resulting in a linear time complexity of O(n). This is optimal since we must examine every element at least once to determine if it's even or odd. Additionally, the algorithm handles edge cases gracefully. For example, if the input array is empty, the pointers will never meet, and the algorithm terminates without error. For arrays containing only even or only odd numbers, no swaps are necessary, and the pointers traverse the array without making changes. Lastly, for single-element arrays, the algorithm terminates immediately since left equals right, and no processing is required. These considerations ensure the robustness of the solution. Let's now focus on the key operations that make this algorithm efficient. First, the even or odd check is performed using the modulus operator. Checking if a number is even, by evaluating number %2 equals 0, is an O1 constant time operation. Next, swapping two elements in the array involves a few simple assignments, which is also an O1 operation. Finally, moving the left or right pointers, whether through incrementing or decrementing, is another O1 operation. Together, these operations ensure that the overall complexity of the algorithm remains linear. To understand this better, let's walk through an example. Consider the input array nums equals 3, 1, 2, 4. Initially, the left pointer is at index 0, pointing to the value 3, and the right pointer is at index 3, pointing to the value 4. Since nums left is odd and nums right is even, we swap these two values. After the swap, the array becomes 4, 1, 2, 3. We then increment left to index 1 and decrement right to index 2 to continue the process. In the second iteration, nums left is now 1, which is odd, and nums right is 2, which is even. Once again, we swap these two values. After the swap, the array updates to 4, 2, 1, 3. We then increment left to index 2 and decrement right to index 1. At this point, the condition left equals right is met, so the loop terminates. The array is now rearranged such that all even numbers appear before all odd numbers. The final output is 4, 2, 1, 3. In terms of complexity, the time complexity is O(n), since each element is checked exactly once, and the space complexity is O(1), as the algorithm operates in place without additional memory. This approach is both efficient and straightforward, ensuring that the array meets the problem's constraints in the most optimal way possible. The provided solution for LeetCode problem number 905, sort array by parity, uses a two-pointer approach for rearranging the elements in the array such that all even integers appear before all odd integers. This algorithm operates in O(n) time complexity and performs the rearrangement in place, optimizing space usage. ###explanation 1. Initialization. Two pointers, left and right, are initialized at the start and end of the array, respectively. The left pointer moves forward, and the right pointer moves backward during the traversal. 2. Main loop. The while loop continues as long as left is less than right. This ensures that the two pointers do not cross each other while processing the array. 3. Swap condition. Inside the loop, we check if the left pointer is at an odd number, nums left, %2 0, and the right pointer is at an even number, nums right, %2 equals 0. If this condition is true, the values at these indices are swapped to move the even number to the left side and the odd number to the right side. For pointer adjustments, after evaluating the swap condition, if the value at the left pointer is even, nums left, %2 equals 0, the left pointer is increment to examine the next number. If the value at the right pointer is odd, nums right, %2 equals 1, the right pointer is decrement to examine the previous number. 5. Termination. The loop terminates when the two pointers meet or cross, ensuring all even numbers are on the left and all odd numbers are on the right. 6. Return result. The modified array is returned as the output. ###edge cases. Empty array. The code handles an empty array gracefully, returning it as is. All even or all odd, the pointers adjust correctly without unnecessary swaps, ensuring the array remains unchanged. Single element. The loop does not execute, and the array is returned as is. This implementation is efficient and concise, achieving the desired rearrangement in a single traversal of the array without additional space overhead. This is the Java implementation of the sort array by parity problem, LeetCode number 905. The logic mirrors the Python implementation, using two pointers, left and right, to rearrange the array in place such that all even numbers are at the start and odd numbers are at the end. Key differences include explicit type declarations for variables and the use of Java-specific syntax for swapping and array manipulation. To begin solving the problem, we start with the input array 3, 1, 2, 4. The two pointers, left and right, are initialized at the start and end of the array, respectively. Initially, left points to 3, and right points to 4. The first step is to compare the values at these positions. Since nums left is odd and nums right is even, we swap these two values. After this operation, the array becomes 4, 1, 2, 3. At this point, we do not move either pointer yet. Next, we recheck the value at nums, left. It is now 4, which is even, so we move the left pointer forward to the next position, which is 1. Similarly, we check the value at nums, right, which is now 3, an odd number, so we move the right pointer backward to the previous position, which is 2. This sets up the next comparison. In the next comparison, nums, left, is 1, and nums, right, is 2. Since nums, left, is odd and nums, right, is even, we perform another swap. After swapping, the array becomes 4, 2, 1, 3. Now, we check nums, left, again. It is 2, which is even, so we move the left pointer forward to position 2. Similarly, we check nums, right, which is now 1, an odd number, so we move the right pointer backward to position 1. At this point, the condition left equals right is met, so the loop terminates. The final output for this example is 4, 2, 1, 3. Now, let's work through the second example with the input array 0, 2, 1, 3. Again, the left pointer starts at the first index, pointing to 0, and the right pointer starts at the last index, pointing to 3. Comparing these values, we see that nums, left, is even and nums, right, is odd, so no swap is needed. Instead, we simply move both pointers inward. The left pointer moves to position 1, and the right pointer moves to position 2. At this stage, we compare nums, left, which is 2, and nums, right, which is 1. Again, nums, left, is even, and nums, right, is odd, so no swap is needed. We move both pointers inward again. The left pointer moves to position 2, and the right pointer moves to position 1. Now that left is greater than or equal to right, the loop stops. The array remains unchanged, and the final output is 0, 2, 1, 3. For the third example, the input array is 1, 3, 5, 7. Here, all the numbers are odd. The left pointer starts at the first index, pointing to 1, and the right pointer starts at the last index, pointing to 7. Comparing these values, both are odd, so no swap is needed. We move the right pointer backward to position 2. Now, we compare nums, left, which is still 1, and nums, right, which is 5. Again, both numbers are odd, so no swap occurs. The right pointer moves backward again to position 1. Finally, we compare nums, left, which is 1, and nums, right, which is 3. Both are odd, so no swap is performed. The right pointer moves backward one last time to position 0. At this point, left is greater than or equal to right, so the loop terminates. The array remains unchanged, and the final output is 1, 3, 5, 7. Through these examples, we can make several key observations about the algorithm. First, it uses two pointers, left and right, to traverse the array from both ends, ensuring that even numbers are moved to the front and odd numbers to the back. When an odd number is encountered on the left and an even number on the right, a swap is performed. The pointers then move inward based on the parity of the numbers at their respective positions. This approach is efficient, operating in O(n) time complexity, as each element is processed at most once. Additionally, the algorithm uses no extra space, making it an in-place solution. These properties make it well-suited for sorting arrays by parity in an optimized manner. The time complexity of this solution can be broken down by examining the two-pointer approach in detail. Starting with the outer while loop, the condition ensures that the loop continues as long as the left pointer is less than the right pointer. Since these pointers begin at opposite ends of the array, they traverse toward the center. In the worst-case scenario, each pointer moves one step per iteration, which means the loop will execute at most n times, where n is the size of the array. Inside the loop, all operations, such as checking the parity of elements using the modulo operator, swapping elements, and updating the pointers, are constant time operations, or O(1). When you multiply the O(n) iterations of the loop by these constant time operations, the overall time complexity is O(n). This ensures the algorithm processes the array in linear time. Now, when you consider the overall time complexity, it is clear that the while loop processes each element of the array at most once, resulting in O(n) time complexity. Shifting to space complexity, this solution is highly efficient because it modifies the input array directly without using any additional data structures for intermediate storage. This means the auxiliary space complexity is O(1). While the input array nums does occupy n space, this is provided as part of the input and not part of the algorithm's memory usage, so it does not count toward the auxiliary space complexity. Therefore, the overall space complexity of this solution is 1, indicating minimal additional memory usage. Examining the best, average, and worst-case scenarios further highlights the consistency of the algorithm. In the best case, if all even numbers are already at the start of the array and all odd numbers are at the end, the algorithm still needs to iterate through the array a single time, maintaining a time complexity of n. In the average case, with a random distribution of even and odd numbers, the algorithm processes each element exactly once, still resulting in n time complexity. Even in the worst case, where all odd numbers are positioned at the beginning and all even numbers are at the end, the algorithm behaves the same way, iterating through the array in n time. This demonstrates the algorithm's predictable and reliable performance across all scenarios. When comparing this approach to a brute force or naive solution, the advantages become more apparent. A brute force method might involve creating two additional lists, one for even numbers and one for odd, iterating through the array to populate these lists, and then concatenating them into the final sorted array. While this approach still achieves n time complexity, it requires n extra space to store the temporary lists. In contrast, the two-pointer solution achieves the same n time complexity but eliminates the need for additional storage by performing all operations in place. This reduces the space complexity to 1, making the algorithm much more memory efficient. Finally, the mathematical proof of the time and space complexity further confirms the efficiency of this solution. The while loop processes each element of the array at most once, and because each iteration involves only constant time 1 operations, the total time complexity is n. Additionally, the algorithm does not allocate any extra memory beyond the input array, which means the auxiliary space complexity is 1. This makes the two-pointer approach optimal in both time and space, surpassing the naive solution by avoiding the need for additional memory allocation while maintaining linear time efficiency. When solving this problem, there are a few common mistakes to watch out for. First, always handle edge cases properly. For example, if the input array is empty, your solution should simply return an empty array without any errors. Similarly, if the array contains just one element, the result should be the same as the input. Overlooking these cases can lead to unexpected runtime errors or incorrect results. Another frequent pitfall is modifying the array in place incorrectly. Many solutions use a two-pointer approach, but improper management of these pointers, such as overlapping or skipping elements, can result in an incorrect arrangement of even and odd integers. Additionally, be cautious not to assume constraints that aren't given in the problem. For instance, the input array isn't guaranteed to be sorted, and it may contain both negative and positive integers. Your solution must handle all these scenarios. Lastly, avoid using extra memory inefficiently. While beginners may opt to create separate temporary arrays for even and odd numbers, this can unnecessarily increase space complexity. Instead, aim for a more optimal approach that balances memory and performance. Another common mistake to note is using the wrong modulo operation for checking odd numbers. For instance, number %2 = 1 works for positive integers but fails for negative numbers because -3% 2 evaluates to -1. A more reliable condition is number %2 = 0, which correctly identifies odd numbers regardless of their sign. Now, from an interview perspective, sorting by parity is often used to evaluate your ability to solve partitioning problems efficiently. A key expectation is the use of two-pointer techniques, which allow you to achieve optimal time complexity of n and space complexity of 1. While brute force methods may work, they aren't ideal in terms of performance. During interviews, you should also be ready to discuss trade-offs. For example, if you choose to use extra space by creating separate lists for even and odd numbers, you'll need to explain why this approach might not scale well for larger inputs. Furthermore, interviewers might ask follow-up questions, such as how to sort even and odd numbers in ascending order, or how to solve the problem in place while preserving the relative order of elements. These variations test your understanding of both efficiency and adaptability. Sorting by parity is closely related to several other problems that also involve partitioning concepts. For instance, LeetCode 75, Sort Colors, uses a two-pointer approach to group elements based on their type. Another example is LeetCode 280, Wiggle Sort, which requires arranging elements alternately, showcasing similar partitioning challenges. Additionally, LeetCode 283, Move Zeros, involves rearranging the array so that all zeros are moved to the end while maintaining the order of non-zero elements. This problem tests your ability to reorganize elements efficiently. Lastly, LeetCode 581, Shortest Unsorted Continuous Subarray, asks you to identify the smallest subarray that needs sorting to make the entire array sorted. Each of these problems builds on the same foundational techniques, so practicing them can improve your mastery of partitioning strategies and help you recognize patterns in similar problems. There are several approaches to solving this problem, each with its own strengths and trade-offs. The two-pointer approach is one of the most efficient methods. Here, you position one pointer at the start and another at the end of the array. If the left pointer finds an odd number and the right pointer finds an even number, you swap them. This method achieves optimal time complexity of O(n) and space complexity of O(1), but it can be challenging to implement correctly due to the need for careful pointer management. Another option is the extra space approach, where you create two separate lists for even and odd numbers and then concatenate them. While this method is straightforward to implement, it uses O(n) additional space, which may not be ideal for large inputs. Lastly, there's the in-place partitioning approach, which involves iterating through the array with a single pointer. As you encounter even numbers, you place them at the front of the array while maintaining their order. This method avoids extra memory usage but requires precise index management to ensure correctness. By understanding these approaches and their trade-offs, you can choose the most appropriate solution for the given constraints and requirements. Great job! We've successfully tackled the sort array by parity problem. Remember the importance of the two-pointer technique for array manipulation, and always aim for efficient solutions. Thanks for joining, and happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!